Hi, ladies and gentlemen. We're going to take a look at one of the most important topics in linear algebra, which is singular value decomposition. This is really the ultimate application that we've been working towards for the entire semester. It's leveraging the information we covered in Chapter 6 with respect to symmetric matrices and eigenvalues and eigenvectors. Let's just jump right in. So these are the three items we're going to talk about. We're going to walk through all of Chapter 7, obviously not today. Today is just Section 7.1. But I want to provide you with a little bit of a background here on singular values and singular value decomposition, how this relates to eigenvalues and eigenvectors, and how it does not. So to start, we're going to take a look at the fact that the big idea here is that singular value decomposition applies to every single matrix. What we were talking about before with eigenvalues and eigenvectors, that only applies to square matrices. We have to have a square matrix in order to use eigenvalues and eigenvectors. So we're going to marry up this idea of eigenvalues and eigenvectors with the last thing that we talked about, which is symmetric matrices. We know that if we have any matrix which is rectangular, we can build, and this is where we're headed with this entire chapter of material, we can build two symmetric matrices, A transpose A and A transpose. Those two matrices have all the advantages of being symmetric. They're going to have orthogonal eigenvectors, they're going to have real eigenvalues, and obviously they're going to be square. So we're going to take the information that we've already talked about and we're going to double down on it with any matrix that we have just by considering A transpose A and AA transpose. The primary decomposition that we're looking at here, the singular value decomposition, which pretty much everyone refers to as SVD, looks like this right here. So, and I've written that out. Here we have U and V, and the U matrix and the V matrix are both orthogonal matrices. They're different sizes. The U matrix is M by M. It's the number of rows square for whatever A matrix we have. V, on the other hand, is N by N. It's the number of columns square. Again, regardless of the matrix that we have. And then very similar to eigenvalues, we have sigma, which is a matrix which has the same dimensions as A, and its non-zero values are called singular values. And we'll talk all about this in just a little bit. The rest of this idea right here that he has in the box, we'll talk about also when we start into 7.1. So it's worthwhile to note that we have two sets of singular vectors. We have right singular vectors and left singular vectors. These are associated with the U and V matrices respectively. So just as it appears where we have it drawn out right here, the left singular vectors are in the U matrix and the right singular vectors are in the V matrix. And we are going to use the V transpose, and we'll talk exactly why we are having to do that in just a little bit. So we have the right singular vectors, and then we also have the left singular vectors, and we'll talk about how we find these vectors and how we do a singular value decomposition. I actually have some additional material that I've included that will just give you a simple example that walks through step by step. That's one thing Strang doesn't really have in section 7.1. He does not have a detailed walkthrough on how we do the computation for singular value decomposition. So there's a little bit more conversation in here about how this actually looks a little bit different in the case where the A matrix is a symmetric matrix instead of just a standard non-symmetric or even rectangular matrix. And then finally, what we're going to do is we're going to talk about principal component analysis. The last idea that we're going to talk about is principal component analysis. And this is really just the idea of how we can apply singular value decomposition to do some feature extraction. And we'll talk about what all of that is. There's one important note here. So Strang talks about the covariance matrix as A times A transpose. And that's because of the way he has defined his A matrix. So when we're talking about principal components, when we take our data and we put it into a matrix, the data generally come with two attributes: features, things about the data. So you can imagine for a home, we could have things like square footage, we could have number of bedrooms, we could have number of bathrooms, we could have number of stories, we could have all kinds of different features about houses. And those features are going to be in our data matrix. And then the other thing we have are samples or observations or experiments. And again, in the house example, we would have multiple houses. Every house has these different features and has different values for the features. So the way that this matrix is generally constructed, and we'll talk about this when we get to 7.3, but it's generally constructed with the features across the columns and the samples as rows. Strang does it exactly the opposite, which is why he's talking about A times A transpose. Everywhere else talks about A transpose times A, and we'll see that. And when we get to section 7.3, it will become clearer. I just want to let you know that's where we're headed eventually in this chapter. So let's just jump right in here for singular values and singular vectors. The decomposition is exactly what we know it is. It's this decomposition here, looking quite a bit like what we saw previously with diagonalization. And that's not an accident. Remember, if A is diagonalizable, we can write x lambda x inverse. And in the case where A is symmetric, so A, in this case, it's going to be symmetric, that's going to be equal to Q lambda Q inverse, but Q inverse is just Q transpose, where Q is designated differently because it is the set of eigenvectors, but these are orthogonal eigenvectors, and we have all the power that comes with that. And in the situation that we have for the singular value decomposition, what we're doing is we are leveraging the ideas of symmetric matrices and positive definite matrices. So we'll look at all of the information associated with the fact that U and V are both orthogonal matrices. Also, it's worth noting that the sigma matrix contains all of the eigen, or not eigen, but singular values, and they are, just by convention, rank ordered. So we always talk about sigma 1 as being the largest singular value. So singular values are always positive, and when we look at how we find singular values, you'll understand why they're always positive real numbers. Of course, they're going to be real numbers because they're coming from symmetric matrices, but they're also positive numbers. One really important piece to consider is this entire paragraph right here. So in this paragraph, Strang really lets us in on what we're doing. He says, we want to go beyond symmetric matrices to all matrices. We want the power of symmetric matrices, but we want to apply it to all matrices. And we want to maintain that orthogonality. So the way we're going to do that is, instead of considering eigenvalues and eigenvectors like we see here, we're going to consider left and right singular vectors and singular values. And we'll talk exactly through exactly how that works. So one thing that we want to make sure that we remember from way back at the beginning of the course is we can take matrices, and then when we're doing matrix products, and we can break them down into the sum of rank 1 matrices. And there's a theorem, the Eckert-Young theorem, which actually says that the singular value decomposition gives us the best approximation to the action of what's happening with an A matrix. And we do that, we grab that best approximation by selecting the largest singular values. So you'll notice we have the singular values here in order, starting with sigma 1 all the way down to sigma r, considering that A is rank r. And we're going to take the associated rank 1 matrices and sum them up for as many as we want, as long as we have the approximation that we're interested in. So it's worth noting that each of these is a rank 1 matrix. And so the matrix A is constructed via these rank 1 matrices, and they are necessarily in the order of importance. The matrix associated with the first singular value is the most important. It contains the most information. And we'll go through some examples of this when we're in class. But it's just critical to realize that we are summing up a bunch of rank 1 matrices, and they are going to provide us with the best possible approximation to whatever the matrix A is doing. All right, this is an excellent example. You're going to want to walk through this example. It does not provide the actual nuts and bolts of how we do the calculations. We'll talk about that a little bit later. But what we want to do is we want to take a look at this construction because it highlights a couple of important things for us. First of all, it gives us the fact that A times V is equal to U times sigma. And then we're going to right multiply by V inverse. A is equal to V times V inverse is, of course, the identity matrix. So we just have the A left, U sigma V inverse. But that's just U sigma V transpose. The inverse is the transpose for V as well as U because they're both orthogonal matrices. Taking a look at each individual vector, what we can see here is that A times V, and I can pick whatever column vector out of V that I want. A times that vector is going to be equal to the associated vector in U multiplied times the appropriate singular value. So just as we did with the diagonalization section, these matrices actually contain the singular vectors as columns. So U has the left singular vectors as columns and V has the right singular vectors as columns. The fact that we have V transpose on the right is because, of course, we've had to right multiply by V inverse, which happens to be the transpose. All of that information is provided here with an excellent example. What I want to do is take a look at what's actually happening and make sure that you understand basically what's going on behind the scenes with singular value decomposition. You remember, and let's just talk about this. You remember when we did diagonalization, we have AX equals lambda times X inverse. And when we did our multiplication of A times Z, that was X lambda X inverse Z. And this on the right-hand side was a change of basis. We changed the basis from the standard basis to the eigenvector basis. And then we did the action of A using the lambda matrix and the eigenvalues, and then we transform back. What's happening with singular value decomposition is almost the same thing, except we have the incredible power of orthogonal basis vectors. Here's the difference. For singular values, we end up with A times Z is equal to U sigma V transpose times Z. Same exact thing. This is just a change of basis, exactly as we did before. Now, however, it's an easy change of basis because the inverse is easy to calculate. So we have this transformation from the standard basis into the right singular vector basis. Then, in exactly the same way we did with eigenvalues, we're going to apply the action of A, which really just comes down to stretching or compressing the vectors that are used on the right-hand side, the right singular vectors. So we've transitioned from the standard basis to the right singular vectors. Now we're going to do our stretching or our compression. And then we're going to transform back, and here's the big difference. We are transforming back with an entirely different basis. So now we take the entity here, just like we did with diagonalization. We've done the action of A, but we're in this other basis. Instead of applying the same basis to get back to the standard basis, we have to apply a different change of basis. We have to apply what's in U. So this is a change of basis from where we did the action of A back to the standard basis. This is a mind-blowing concept when we start to think about it. We can easily understand in the eigenvector world where we went from the standard basis to the eigenvector basis. We did our action and then we went from the eigenvector basis back. What's happening with singular value decomposition is not nearly as easy to picture. We are taking the basis and we are transforming from the standard basis to the right singular vector basis, but we're in this space that's not necessarily well defined. We do the action of A, but now to transform back from this kind of bizarro area where we've done the calculation, we use a completely different basis. And that's what gets us back to the standard basis. So this place that exists in between the right singular vector basis and the left singular vector basis is where the action is happening for A. It's a difficult thing to visualize. You just kind of have to believe that this is happening and work through the mathematics and believe that the mathematics is correct, because it is. We're going to rotate. So that's our change of basis. The beauty, again, of having an orthogonal basis is we just rotate the standard basis into our right singular vector basis. Then we do our stretching, our action of A, if you will. And then we're going to rotate again because we have another, with the left singular vectors, we have another orthogonal basis. So we do another rotation, but it's a different rotation than we did in the beginning. Let me show you a demonstration of what this looks like. So specifically here, Strang provides us with several questions, and we're going to walk through these to help build our understanding. Let me just highlight all of these, all the questions have to do with this idea right here. And he's provided us with a specific example, and that's what I'm going to walk through for you, is the specific example here. But what he's really done, we still have A is equal to U sigma V transpose. In this case, we have a square matrix, so it's a little bit difficult to see necessarily how this would be different from eigenvalues and eigenvectors, other than the fact that we're using two different bases, not just one. But we want to take a look at what he has to say here. We have a rotation of 30 degrees, right? That's a rotation on the output side, right over here. And then we also have a rotation of 60 degrees, and that's rotations over here on the input side. And so what we're going to do is we're going to take some vector z. So we're going to take A, and what I'm going to show you is actually done on, just like Grant Sanderson tells us. If we understand what's happening to the standard basis vectors, then we can understand what's happening for the entirety of the R2 plane. So we're going to apply the transformation of A to some vector. The vectors are going to be the two standard basis vectors, I hat and j hat, and that's going to be equal to U sigma V transpose Z. And so this is our change of basis. We're going to go from the standard basis and we're going to rotate, and it says we have a positive rotation of 60 degrees. That's going to be counterclockwise. So what is the inverse of that? Because remember, V transpose is the inverse. So what is the inverse of a counterclockwise rotation of 60 degrees? It's a clockwise rotation of 60 degrees. Then we're going to do the action of A, and then we're going to transform again. We're going to transform with a rotation of 30 degrees, and this 30 degrees is counterclockwise. Let me show you what that looks like. All right, so what I have here is MATLAB setup. I have the two standard basis vectors. I have I hat here and j hat here. And the action that's provided by this matrix right here gives us the two blue vectors. And what I want to do is just demonstrate for you what's happening with the singular value decomposition. So the first thing that's going to happen, sorry, I hit the wrong button there. The first thing that's going to happen is the rotation. We have the 60-degree clockwise rotation. So the standard basis vectors have been rotated to the magenta. Now what we're going to do is apply the two singular values. In the x direction, we're going to double the value. So we're going to double the value here from, around 0.85 or so out here. And then we have a stretch of just multiplication by 1 in the y direction. So the y direction here is not going to shift. This is just going to stretch out with no change in the y direction. Similarly, for the rotated I hat vector, that's going to double from 1/2 to 1. But in the y direction, this way, nothing's going to change. It's going to stay at the same place. So the green vector set of vectors, those are the vectors after we've applied the stretch. So we rotated to the magenta, we stretched out to the green by doubling in the x direction and multiplying by 1 in the y direction. And now we're going to take those green vectors, literally the green vectors, and rotate them counterclockwise by 30 degrees. And when we do that, we end up with, whoops, sorry, we're starting over here. It jumped forward on me. So we did the rotation, we did the stretch, and now we'll do the rotation back, and we end up with exactly the blue vectors we have. So this is what singular value decomposition is doing. It's finding a location between two different change of bases where the action of A is diagonalized. And because we have the freedom of two different bases, a basis on the input side and a basis on the output side, the right singular vectors and left singular vectors respectively, because we have these two different bases, we can take any rectangular matrix, no special requirements, and we can diagonalize it. And because we can do the diagonalization, then the calculations are easy for us. All right, so this is what's happening in question 2. So question 3 is just an expansion on question 2. Question 4, he gets back to really what's happening with question number 1. And what he says is, hey, if the matrix was symmetric to start with, so if we have this decomposition, the SVD, but we started with a symmetric matrix in the first place, that would have to be a square matrix, of course. And then because it's symmetric, we already know that a symmetric matrix is going to be Q sigma Q transpose. Right? That's what we're gonna end up having. We're going to have this transformation where the basis, the change of basis, is the same on both the input and the output side. Remember, for every symmetric matrix, the column space and the row space are the same. Okay, let's take a look at the reduced form, also known as the economy form of the singular value decomposition. What I want to do is just walk through the sizing, give you an idea of kind of what it is we're talking about. Imagine for a minute that we have A, and A is some matrix with a whole lot more rows than columns, just as an example. So in this case, A would be U, and U would be M by M. And this is the U matrix. And then the sigma matrix is the same size as A. That's M by N. This would be sigma. And then we would have the V transpose matrix. V transpose. And V is n by n. And now we kind of want to think about what's going on here. The sigma matrix, remember, we always have sigma 1, sigma 2, however many of these we have for the rank of the matrix, and then possibly some 0 values after that. And for this tall, skinny matrix, we would have this situation where we have the top part, which would be n by n, so kind of the n by n portion of sigma, would be square and would have the non-zero singular values as well as the zero singular values. It has all the singular values. The stuff that's below it is just a rows and rows of zeros, however many rows and rows of zeros we need until we get all the way down to a full matrix, which is m by n in size. Think now, if we grab one of these vectors and we multiply it times u, so we grab that vector and we multiply it times u, we would come down and all we would have is sigma 1 times u1. That's it. We grab the next one, we'd have sigma 2 times u2. We keep going until what we've done is we've gone through all of the columns of sigma. And once we've done that, we will have ended up multiplying the first n columns of u. Well, what does that mean for the column space of A? It means that the column space of A is contained inside of those first n columns. Well, all of the columns of U are orthogonal. So what would the rest of the columns of U have to be? What is the vector space that is orthogonal to the column space? Remember the 4 fundamental subspaces. This would have to be a basis for the left null space. So when we take the span of all of these vectors from u vectors from 1 to n, that's going to be a basis for the column space. And then when we take the rest of them, n plus 1 out to m, that's a basis rather for the left null space. So this is the way in which we can think about and actually shrink down SVD. This is where the whole idea of an economy SVD comes from. What we're going to do is we're going to get rid of all of the 0 rows that are in our sigma, as well as all of the 0 columns. And in order to make the multiplication work out, we're going to shrink everything down accordingly. So in this case, what we've done is we have kept a little piece of sigma here, which we call sigma r. It is rank by rank. Well, in order to make that work, it's going to have to multiply only by the first r vectors in U. So we have our sigma r, which is multiplied times something that is the same rank as A. This is UR. Those columns span the column space of A. Then what we need to do is we have to think about what are the pieces of V transpose that we're going to keep. Well, any vector that's in V transpose that we multiply times our sigma r is going to lose stuff on the bottom. And so what we're going to have in this situation is we're going to have VR, and let me erase the size of sigma r there, and the VR is going to be r by n. Right? And so let me just grab this and move it into position here. And it's going to look like that. So what we end up with then, when we do the economy, the reduction, in order to not carry around all of the zeros. Not to say that that information is worthless. It certainly is not. We were able to, for example, grab out the span for the left null space. That's great. This is actually how it's done when we're looking at finding a basis for the left null space. But what we have left over then, we erase this, is we have a smaller piece of information. We have an R by R matrix here. Here we have an R by N matrix, and here we have an M by R matrix. And this contains just the essential non-zero information for A. So all of this I've done for the situation where we have a tall, skinny matrix. What I want you to do is to do exactly the same thing for a matrix that is wide, right? One that is short and wide. And you can look through here. He talks about how we do all of the reduction, if you will, for the fact that we don't have a square matrix or we don't have a full rank matrix. So proof for the singular value decomposition. Of course, we don't do any proofs, but there are, particularly from these two lines, there are some really important items to be gleaned out of that. Right? And so all this really has is, assuming we're going to start with A is equal to U sigma V transpose. And again, we're not doing the proof. We're just going to say that that works. And then what they do is they simply walk through the fact that A transpose times A would have to look like the product that they've provided. So A transpose times A is going to be this. But we know that this piece here, U transpose times U, is the identity matrix. And so what we're left with then is sigma transpose times sigma. And we'll talk about that in just a second. On the other one, we're left with V transpose times V, which is also the identity. So what we're really left with considering is what's sigma transpose times sigma, or sigma times sigma transpose. In either case, we're going to end up with a square matrix. These matrices are symmetric. However, the only non-zero values are on the diagonal. So we're going to end up with the diagonal values squared. We're going to have sigma 1 squared, sigma 2 squared, etc., down to sigma r squared. And then we're going to have zeros for however far this goes. This is going to be the form for sigma transpose times sigma, or sigma times sigma transpose. How many zeros we have to do with the dimensions of the matrix. But we're going to end up with all of these zero eigenvalues. And so this leads to the information about how we actually do the calculations. And there's an example that's provided, and he provides it right down here that you should walk through. What I'm going to do, I'm not going to walk through an example. That is something that I've included in the material for today's lesson. It's an attachment, and you'll be able to walk through and see exactly how it's done. But let me just say the two steps that we go through. The first thing we're going to do is build A transpose A. And we're going to solve the eigenvalue problem associated with A transpose A. What that's going to give us are the right singular vectors. So solving A transpose A is going to give us eigenvalues and eigenvectors in the following way. A transpose A V I for each eigenvector is going to be equal to VI times lambda, but that lambda is going to be the singular value squared. And the singular value squareds, you see them here on the diagonal, that's what we're going to find. So from this, we can gain the information for the right singular vectors and the singular values. Then what we're going to do is we're just going to solve directly for the left singular vectors. We're not going to do this again. We're not going to solve the eigenvalue problem twice. It's too much work. What we're going to do instead is make use of this equation here. And so the question is, where does that come from? That just comes from the definition of singular values and singular vectors. Remember, A times any right singular vector is equal to the left singular vector times the singular value. And so it's easy for us to see that if we want the left singular vectors, all we have to do is divide both sides by the singular value. And we cancel those out and we end up with this equation right here. That's the process that we use to solve. Now, what we're going to do is MATLAB. MATLAB has a singular value decomposition command. That's what we're going to do. But this is the process for the small problems that are going to be in the exercises where we're practicing this by hand, just like we did the 2x2 eigenvalue eigenvector problems. We're going to practice some small problems using this process. So make sure you're comfortable with that. And that's what he talks about in here. And he provides a really nice example that you want to walk through in full detail. And remember, I'm also going to attach an example for you. So a really important piece here is this whole notion of the four fundamental subspaces. And he walks through this and he reminds us that we're able to do these calculations because those two things are true. The fact that the column space, which is defined by those first columns of U, is automatically orthogonal to the left null space, which is going to be the rest of the columns in U. And that's the same with the rows in V transpose, which are the columns of V, of course. So the rows in V transpose are the columns in V. And what we have is the same type of thing. We have the row space and we have the null space. And the first set of right singular vectors in V, that's going to be associated with the column space. With the row space. And then the remainder are orthogonal, and those will be the null space vectors. So here's just something you can read quickly. This is not so much of interest to us because we're more interested in the application problems. So what we are interested in is this item right here. This is the way in which actually we end up solving for singular values and singular vectors. And it's also really illuminating, and it provides us with good information about this last topic down here. What we're going to do is we're going to look at the fact that, hey, if we started, and let me just orient you to what I'm going to show you in just a second. If we start with our two vectors, I hat and j hat, and we start rotating these. So now we're just talking about 2x2 matrixing, just a simple 2x2. The idea, however, expands out no matter what size matrix we have. We're going to start with I hat and j hat, and we're going to rotate those vectors, just like the example that we looked at initially with the MATLAB image. We're going to rotate those vectors until the output vectors are orthogonal. Remember what we're doing. We're looking for two sets of basis vectors where each of them is a change of basis. We want to change from the standard basis through a rotation to some particular basis that allows us to diagonalize A and have on the output side another orthogonal basis to transform back into the standard basis. Let me show you what this looks like. All right, what I have here is the input, the I hat and j hat vectors here in red, and the associated output vectors, just like we were talking about previously. But now what we're going to do is we're going to start rotating the input vectors. And as we rotate the input vectors, you can see, right, we're changing V. V was initially the identity matrix. But now we are doing the rotation exactly as Strang talks about in his question number 2 up above. That whole set of questions is associated with this type of a situation. So we're continuing to rotate, and what we're looking for a singular value decomposition, we're looking for the place where the blue vectors become orthogonal. And what you'll notice is as we continue to move around here, we're at 6 degrees. We're not quite there, but we're getting closer and closer and closer. And as we move towards 50 degrees, we see that when we're at a 50-degree rotation, that's our change of basis. So our new basis vectors are these red vectors. We've rotated the standard basis to the new input basis. And the output basis is orthogonal as well. This is the situation we're looking for singular value decomposition. Whatever the matrix A is that is doing the action for this situation is taking these orthogonal vectors and is giving us orthogonal vectors back out again. Let's continue and show this. We're going to just play it. And what you'll notice is that as we rotate through with the input vectors, we end up drawing an ellipse. This is only because we have a 2x2 example, and I'll show you a 2x3 in a little bit. Actually, it's a 3x2 matrix. But what you see is, let me start it over. What you see is, as we rotate through, we are looking for the place where the output vectors, the column space vectors, are orthogonal to one another. And that occurs at 50 degrees. You'll notice it also occurs at a couple of other places. Let's dig into that a little bit more. This is at a different A matrix. So same thing, we're going to rotate. We're going to rotate through. And as we're rotating, you can see the output vectors. And the output vectors are changing until we get to 40 degrees. And at 40 degrees, the output vectors are also at right angles. These are the two change of basis vectors that we have. We have a rotation that's going to get us to the red vectors. Then we're going to apply the action of A, and then we have another rotation that's going to get us to the blue vectors, which are orthogonal as well. This is the whole point of what we're doing with singular value decomposition. What you'll notice is the singular value decomposition is not unique. Right now, the blue vectors are orthogonal. What if we add 90 degrees to the current 40? What if we go out to 130 degrees? Well, we'll work our way out there. And we're getting close. 130. We have another place where we have orthogonal vectors. And if you think about it, if we add another 90 and go to 220, we're also going to have an orthogonal set of vectors. Let's back up to 220. And we have our third set. There's always going to be 4 in this 2x2 example. And let's look at why that is. Think about A is equal to U sigma V transpose. Well, in the 2x2 case, that's a 2x2 matrix. This is a 2x2 matrix. This is a 2x2 matrix. We have sigma 1 and sigma 2 here. If we have, remember, eigenvectors, and the singular vectors are the same because they're really just the eigenvectors of A transpose A and AA transpose. To have an eigenvector, we can multiply by -1 and we still have the same eigenvector. That's true here. We could multiply U1 times -1, and if we multiplied V1, the first column of V, by -1, we'd have the same answer because, remember, we've built just a bunch of rank 1 matrices. This A matrix is equal to sigma 1 U1 vector V1 vector transpose, that's an outer product, plus sigma 2 U2 vector V2 vector transpose, that's another outer product. So if we multiply both U1 and V1 by -1, we get the same answer. The same thing, of course, is true for U2 and V2. So that's where 2 of our 4 options come from. 2 of the 4 options in the rotation thing, remember we saw 4 different ways that we could set up an orthogonal input and have an orthogonal output. So we could change the signs on U1 and V1 or U2 and V2, and the other options come from the fact that we can swap sigma 1 and sigma 2. By convention, we always have sigma 1 be the largest value, but it doesn't have to be that way. We could have swapped sigma 1 and sigma 2. That would swap the columns in U and V, which would swap the columns in U and the rows in V transpose. And then we could do the 2 different signs again. That would give us all 4 options. That's why we have 4 options for the 2 by 2 case. So it's important to understand that we do not have a unique answer when we are finding singular value decomposition. Let me just show you the 3-dimensional example. So the 3-dimensional example is here. This, now we have a 3 by 2 matrix. So the input is in 2 dimensions and the output is in 3 dimensions. And you can see as we work through here that we're going to end up with the same type of thing as that we had before. Okay? And there's a place, and for this one, it's around 85 degrees, where the input, of course, is orthogonal. And that's all we're doing is just rotating. We're maintaining that original orthogonality with standard basis vectors, and we're just rotating. And we have a rotation out here. Now, this may look 3-dimensional, but the way I've built the diagram is actually normal to the plane that contains these 2 vectors. So this is the actual perspective of what this looks like for the ellipse right here. All right. You can imagine, and this is the way it's done, right? So if we have an image which is 1,000 pixels by 1,000 pixels, we now have a standard basis with 1,000 vectors in it. So we have 999 ways to rotate those 1,000 vectors. And this is what we do. We rotate those looking for the place where we end up with orthogonal outputs. We can't do it all at the same time. We have to peel them off one at a time. And that's really what this conversation down here is about. So we're going to find our first singular vector, and this is the right singular vector, by maximizing this ratio. So let me be clear because, and I'll explain my goofy baby face there in just a second. So I'm going to use the z again, because these are not, we're not talking about eigenvectors. What we're trying to do is maximize this quantity. We want this to be as large as possible. And we talked about something like this when we looked at symmetric matrices. However, what we're going to do is we're going to pick z's to be univectors. And if the z is a unit vector, then it has a magnitude of 1. So what we're really trying to do is we're really trying to maximize this quantity where the magnitude of z is just 1. Z is a bunch of unit vectors. And once we find that, once we find the z vector that actually maximizes this thing, then that z is v1. It is the first right singular vector. Let's go back to the picture for a second because it becomes very clear in the picture that this is true. Think about the shape that we're drawing with the output vectors here. Right? What we're doing is we are drawing our ellipse and we are finding the place where that output vector is maximized, right? Where this length is maximized. And once we find that, then we have found the correct rotation for the input vectors, and that's what's maximizing this value that we're talking about right here. So we are searching around for the place that maximizes A times V. And what are A times V's? Those are the outputs. So we're looking for the longest possible blue vector. And as we can see, that happens at the same point in time because of the ellipse when the vectors are orthogonal to each other. The output vectors, the blue vectors are orthogonal to each other. This is the method to find what we're doing. So the reason for the face is because, and listen, you know, this is just the way math textbooks are. I apologize. It's unfortunate. We have silly stuff like this, where Strang says, write any vector x as this linear combination of x vectors. Okay, that's ridiculous and hard to follow. What he's saying is, pick any vector z and write it as a linear combination of the x vectors. So the z is a c1 x1 plus c2 x2 plus etc. for all of these. Well, the C is not the vector, X is CN, vector, right? And we're doing this linear combination. That's for the Rayleigh quotient conversation, which we're not really going to get into, but it's made even more confusing because this first X is missing its one subscript. So now we have X's in both places, and hence we end up looking like this. Okay, more conversation here about how we would continue to find the next right singular vector as we walk through this process. Down below here, we have the conversation of comparing singular values and eigenvalues. Okay? And so what it says is, why are all eigenvectors of a square matrix less than or equal to the largest singular value? Sorry, eigenvalues. Why are all the eigenvalues of a square matrix less than or equal to the largest singular value? And he walks through and discusses this. This is not so important for us. This is, it's an important topic, but probably something that you'll learn later in your second linear algebra class. And then finally is a conversation here about computation, which we're not so interested in. So let me just review quickly, right? We have singular value decomposition, which is nothing more than eigenvalues and eigenvectors applied to a modification, if you will, of any matrix that is given to us. If we have a matrix, regardless of whether it's square or rectangular, semi-definite, positive, semi-definite, none of that matters. We just take it and we build A transpose A, and with A transpose A, which we know is symmetric, we can find eigenvalues and orthogonal eigenvectors. And then using that information, we can build another set of eigenvectors for A transpose. And using these two sets of eigenvectors, which are the singular vectors from the eigenvectors from A transpose A and A transpose, we use those two sets of vectors as our singular vectors, and we take the square roots of the eigenvalues to come up with the singular values, and we have this incredibly powerful transformation. And it applies to every single matrix that we can possibly run into. So let's take a look at the questions for today. This is really just taking a look at what's happening with singular value decomposition. Here is a conversation about column space, and then a problem here for you to think about. That's it. Look forward to seeing you in class.